So, as said, my name is Michal, and she suggested in a mail that the guest lectures introduce the journey into explainability. So here's mine. I finished my PhD at the Hebrew University, and then I went to UCSD for Postdoc, and there I accidentally came across explainability, and I just thought it was really interesting. And fast forward a few years, I just came back from a workshop at UC Berkeley on explainability. So in the last few years, this is what I've been working on. And I really love explainability because on the one hand, it's an important topic. Now that machine learning is entering our lives and making critical, life-changing decisions, we should understand the models better, what the reasoning. So it's an important topic. But on the other hand, we don't really understand. The foundations of the field is missing. So as a researcher, I get to participating in laying down the foundations, which I found really exciting. Okay, so this is a little bit about me. I would be happy to get to know you a bit. So who is a student? Student. Can see some that don't represent. Who is from the industry? Okay. Who worked on clustering before? Okay, so this is the topic of the talk today, interpretable clustering. Okay, so what I'm going to talk today is going to be a bit different from what you've seen so far in the course, in different perspectives, different dimensions. So, in first dimension is the question of how the model was produced. So, usually, when you talk about line and shell and dice, then you consider the model which was built in a supervising learning fashion, which means that each example has a label. In here, in a clustering problem, we are talking about unsupervised problem, and examples don't have labels. Okay, so this is one dimension which is different from what you learned so far. Another dimension that what we're going to see today is different from what you've seen previously is explainability versus interpretability. So by interpretability, I mean that the model itself is self-explanatory, it's simple, and we understand what's going on, so we don't need extra data, versus explainability, where we usually add post-hoc explanation, and we try to understand a given model, which is black box usually. Okay, so this is a different version, a different dimension, either explainability or interpretability. So line and chart is an explainable model because we get function and we want to add information afterwards. For example, feature attribution. Interpretable models is well the model itself. So a third dimension, which is different from what we've seen so far, is the concept of heuristics versus guarantees. So in line and in chart, and in many methods in the field, usually there are heuristics. There is some method which hopefully are good. Maybe on some data sets that you see on the papers, they are good, but maybe on others, they aren't. We just don't know. We don't have any guarantees. So we have heuristics. What I'm going to show you today is a method which has provable guarantees. I'm going to show you a method that works for any data set. So those are the two three distinctions between what we are going to talk about and what you've seen. It's going to be for unsupervised learning, for clustering. It's going to be interpretable models, and we are going to talk also about guarantees. Okay, so what is clustering? In clustering, we are given a set of points. So in here we have circles. Each blue circle is its own point. And the goal is to have some high-level view across the end of what's going on. We want to somehow partition the data into small number of parts in order to understand what's going on. People use it to sometimes get a sense of the data set that we have in front of us. So this is a very simple data set because in this picture there are only two features, X and Y. But when we usually have many features, it's unclear exactly what's going on in the data set, and clustering is becoming more important. So here is an example of clustering into 5 parts. So this is a nice clustering, but the problem with it is that when you get a point and you want to understand why it's in the first cluster, for example, it's not really clear. It's some complex computation. In here, it might be a bit clearer because someone can say of X and Y, but usually, again, we are thinking about high-dimensional data. There is this complex decision, and you just don't understand what's going on. So, given a point, we want to understand why the clustering decided to put one point in a specific cluster and not the other. Okay, so this is the what we want to understand, what we want to explain. And to find an algorithm that does exactly that, I'm going to describe a work that I did with my collaborators, Sanjay Dashgupta, Robert Frost, and Simon Strachler. And it was published in ICML 2020. So for those of you who don't know, ICML is one of the top conferences in machine learning. And the paper is called Explainable K-means and K-medians clustering. Okay, so we started that we want to find clustering which is interpretable. But what exactly do I mean by interpretable? What do I mean exactly by something which is self-explanatory? So here is one example of some of diagnostic from our day-to-day life. So suppose that you want to understand whether someone has COVID. So we will start with, for example, testing the temperature. And then we'll see, is the temperature high? Then we will do one thing. If the temperature is low, we will do something else. This thing is pretty clear. We understand what's going on. What makes it so clear? So basically two things make it clear. One, this is a small flowchart. It's not something which is too large. And second, at each node, at each inner node, there is simple question that we are asking. And this is what we want to have. We want to have an interpretable clustering. What does it mean for clustering exactly? So remember that this was the clustering that we had previously, the unexplainable clustering, which we didn't understand what's going on. And here is an example of another clustering. Okay, so on the right, what you see is interpretable cluster. So let's look at this. So on this graph, we see a decision. Each leaf corresponds to a different cluster, one of the 5. In each inner node, we compare one feature, in this case, either X or Y, and compare it to some threshold. So let's look at this clustering. on the root. So at the beginning, we compared x to 4.5. If x is bigger than 4.5, then the cluster label is 2. Now, this decision tree is visualized using this graph. So when x is bigger than 4.5, the cluster is 2. So in here, you see the orange color. Everything where all the points where x is bigger than 4.5, we had an orange color. And then we continue in this way, and we compare the y to minus 4. If it's bigger than minus 4 and let's say bigger than 4, we get exactly cluster number 1. So this is the kind of model that we're looking at. So we have a decision tree. In each inner node, we compare a feature to a threshold, and the number of leaves is the number of desired clusters. In this case, 5. So in this case, for this data set, this clustering looks pretty good. So we have an intertopological clustering for this data set. But we might wonder how to do it generally. How can we take any data set and build such intertopological clustering? This is one question. How can we find and design an algorithm for that? Question that we might ask ourselves is the resulting intertopological clustering is good? Is it close to optimal? Maybe once we have an intertopological clustering, then the cost is huge. We have a really bad cluster. So those are the 2 questions that we are going to discuss. First, we are going to talk about a new algorithm. So just notice that, as I said earlier, the number of leaves that we want is the smallest possible. Okay, so we want to understand how to build such a clustering for any data set. And second, what we want to show, we want to have provable guarantees. We want to know that once we use this algorithm, the quality of the clustering is not too bad compared to the optimal. So let's see how we do those things. So here's the new algorithm, which we call iterative mistake minimization. This is a pretty simple algorithm. It has 3 steps. In the first step, it uses some unexplainable clustering, some way to have to take all the clustering and just partition it to K clustering in an uninterpretable way. Then we take each point and just remember what is the cluster that relates to this point. Okay, now comes the more interesting part. What we are going to do, we are going to build our tree on the root from the top down. And each step, we are going to find some cut. We are going to define some thresholds and some feature, and going to create this inner node and continue in this way. How we are going to choose which threshold and which feature to take? The idea is to take the cut with minimal number of mistakes. So mistakes is a new notion that we define. So here is the formal definition of what a mistake is. So if we have some inner node is defined using a feature and a threshold. So a point is a mistake for this node if both the center and the point reach this node, and then they are going the other way. So there is the center that we found in the early steps. Remember, for each point, we have the optimal center of this cluster. And now we are going to see if the same point and center reaching same label. And then instead of going in the same direction, they just split. And then we are saying it's a mistake. So let's see a visualization of what's going on. So here is a data set. And we apply the algorithm with k equal 5. We want 5 pallets in this class. At the beginning, what we did is run an algorithm and a clustering algorithm and followed each point with the corresponding cluster. And we also have the different centers of the clustering. So we have the 1 here is the center and 2 and so on. Okay. Now, when we have this, we're ready to run the new algorithm. The algorithm runs from the top, from the root down, and at the beginning, it checks all the features, in this case, x and y, and compare it to all possible thresholds, and choose the one with minimum number of mistakes. In this case, in the first split, choosing the feature x and the threshold 5.5, there was only one mistake, so we choose this. Then what happened is that center 1 went to the right, and all the rest of the centers went to the left. So we finished with the right subtree. So we are moving to the left, and we are continuing in the same way. So this is the algorithm.
So here you are labeling each data point with the corresponding cluster.
Exactly.
So it means that in first step you are labeling each data point with the name of cluster. And once you have labeled the data, so if you can simply apply decision tree classifier over that label the data. So is that decision tree will be different from this decision tree?
Actually, this is a great question. So our first attempt was to do exactly that, to do like a supervised learning problem and run ID3. Then we found an example where this is going to be really bad. I don't have the example with me, but I can show you offline.
So it means that you are actually not directly applying the decision tree classifier over this, but you are proposing your own algorithm, just kind of a tree classifier.
We are designing a new classifier in a way. We are not using the popular ID3 algorithm. This one. If you're going to do efficient implementation of this algorithm using dynamic programming, the running time of this algorithm is going to be really fast, only k, d, n log n, where k is the number of clusters, d is the number of features, and n is the number of points. So notice this is really fast because the input is of size dn. For each point, we need to represent all features. And KDN is a kind of a minimal number in a way because k-means is doing KDN at each step. So this algorithm is really fast. Okay, so let's see how this new algorithm behaves on empirical data. So what we did is compare this algorithm on some small data set and some larger ones. And what we did is compare a new algorithm, the IMF, to 3 different algorithms. So ID3 is labeling the data and then running ID3. And qubit and CL3 are different algorithms to find the clustering using trees. What we did is in each cell, we took the value of the k-means value of the clustering, and we compared it to the optimal one just by using Python k-means function. So we want this function to be as small as possible and preferably close as possible to 1. And what we see is that our algorithm beats the computation. Okay, so the quality of the algorithm when k-means cost is pretty small. And
in this case, what 1.04 efforts?
So what we compared is the k-means cost like the distance, I will talk about it in a sec, but the distance between each point to its center square, and compare it to the optimal unexplainable clustering. So we want to be as close as possible to the unexplainable clustering, k-means wise. Okay, so I'll do it quickly. Running time. So we compared it to the k-means algorithm, and just remember, to be fair, the k-means algorithm, the Python implementation was a lot of people try to implement it very efficiently, and even though it's really, really fast, we are still very, very close to them running time-wise. So this IMM algorithm is fast. Another example of what to do with IMM is, let's run it on real data set and look on the resulting output. So we took the hog type data set and sorry, the 20 news book, and we just focus on four subjects. So we focus on like hardware, space, Christianity, and Facebook. And then we ran the algorithm. And we saw that the algorithm decided on taking the feature space and then deciding that it's related to space, which makes sense. And looked on Jesus and decided that it's related to Christianity, which makes sense. Plus now we know exactly how the clustering is being performed. Okay, so we saw a new algorithm, the IMM algorithm, which is fast, and on some data sets that we checked, the result seems great. But how do we know that it's going to be good for any data set? So this is the second question that we were interested to have some provable guarantees. So just one slide of equations. This is the k-means cost that I've been talking about. We are taking each point. We're going over all clusters, so we have sum from I equal 1 to k. In each cluster, we are going over all the points in the cluster, and we calculate the distance of x to its center square. And in k-means cost, the best center is the mean of that cluster. So this is why we have this cost function. This is k-means cost. And now, after defining how good clustering is, if we want to prove that an algorithm is good enough, we need to measure exactly what is good enough for us. So for that, we have the idea of a approximation. So what is an approximation algorithm? So we say that an algorithm is an A approximation if the cost of the clustering is at most 8 times the optimal cluster. We want A to be as small as possible, preferably 1. So this is a measure of whether we did a good job or not. Okay, so here comes the cool thing. What we were able to show is that IMM is O of k squared approximation. What does it mean? It means that no matter which data set we will get, our k-means cost is going to be at most O of k squared times the optimal one. And notice that this approximation does not depend on the number of points that we have. It's not important how many features we have. And we know that no matter what happens, the IMM algorithm is going to return an algorithm which is most O of k squared. So we have provable guarantees that IMM can go to 1. So I want you to really appreciate what's going on. So let's look at an example of when k equal 2. When k equal 2, it means that we want the decision tree with 2 leaves. This means only one inner node. This means that we are designing our clustering based on only one feature and one threshold. That's it. Interpretable clustering for k equal 2 means that we get a point and just look on one feature and one threshold. So this is very local. The very surprising thing is that we are able to show that even though it's so local, the k-means cost is at least most 4 times the optimal one, which is crazy because at the beginning, when I started this project, we all thought that maybe the cost is going to be infinite larger than optimal, because this is a really hard constraint to have an interpretable clustering. But apparently, not so much. And so this is our results. And so following our work, there were several follow-up works trying to improve our lower bounds and our upper bounds. Okay, so just to summarize, so what we talked about is a new algorithm that finds an interpretable clustering. This is the first algorithm that has provable guarantees that only depend on k for k-means cost. I showed you upper bound, but we also talked about lower bound. And the algorithm is good in practice, both fast and small cost, and you can check our GitHub code and use it. So that's it. Thank you. Sure. And if you have some cool application of this algorithm, feel free to mail me and tell me about it. I will be excited.